over the course of my career. And they're some of the smartest and kindest and most ambitious people that I know. So it's a pleasure to be here. Just a personal note that I've had contact with people from India since I was about 12 years old, because my parents hosted an exchange student, an Indian exchange student, who was a Sikh. And we became friends one day when I said, "What's underneath your turban?" And he said, "I'll show you." And he unwrapped it for me and laid out his hair, which was probably about 2 meters long. Okay. So my subject today is gravitational waves. This is the most exciting topic in gravitational physics. Worldwide, about 1,500 scientists are working on this. The picture behind me here shows a computer simulation of the gravitational waves emitted when two small black holes merge to form one large black hole. And by the end of this decade, we expect to directly observe this kind of process using gravitational waves. So in my talk, I'm first going to describe the fundamental physics. What are gravitational waves? I'll show you how the modern detectors work. I'll tell you something about the important sources of gravitational waves, what science we can do. I'll tell you about the next generation of detectors, perhaps I should say the current generation of detectors, because they just started operating last month. I'll talk a bit about sources that we might also see in electromagnetic radiation, and if there's some time, I'll talk about the longer-term future. I know this seems like a very formal setting, but if you want to ask something, I'd be delighted. So just put up your hand or shout if something I say isn't clear. So my first topic is gravitational waves. What are they? How are they produced? So the ideas behind gravitational waves had their origins in Einstein's work in 1905. As you know, Einstein's special theory of relativity, which he published in 1905, has as one of its fundamental concepts that nothing can go faster than the speed of light. And this discovery in 1905 created a problem. And the problem had to do with Isaac Newton's universal law of gravitation. Because in Newton's law of gravitation, gravity is instantaneous. There's no delay for propagation. So let me illustrate this incompatibility. The Earth orbits the sun in a circle. It's about 150 million kilometers in radius. And it takes light about 1,000 seconds to cross this entire circle. So now, you know, I think most people here have a scientific background. You know that if something moves in a circle, that means the acceleration is towards the center of the circle. And so here, the center of the circle is the sun. But where is the sun? If you look in the sky, you can see the sun. But if you think about it, you're not seeing the sun where it is right now. You're seeing the sun where it was 8 minutes ago. And so, suppose we measured the acceleration of the Earth as it goes in this circle. Would that vector point towards where we see the sun right now? In Newton's theory, it wouldn't. It would point to where we'll see the sun 8 minutes from now. And so, Newton's theory is not consistent with Einstein's special relativity. And it took Einstein about 10 years to sort this out. And so the modern description of gravity, Einstein's general theory of relativity, was discovered or invented in 1915. It resolves this incompatibility. So in general relativity, mass and energy curve the geometry of space-time, as shown here. And particles, like light, travel along the shortest path in this geometry. So for example, a star might be here. Sorry, a star might be here, pardon me, but gravity curves the ray, the path that the ray follows, so somebody looking actually sees the star somewhere else. And if you have rapidly moving masses, then the gravitational effects of these travel away at the speed of light. And you get waves in the geometry which move away from the source at the speed of light. So these are called gravitational waves. Now, gravitational waves carry energy, but they're very weak. And a formula for the luminosity of gravitational waves has a very tiny factor in front. It's the square of the third time derivative of the quadrupole moment with this tiny factor of Newton's gravitational constant divided by the fifth power of the speed of light. And that number is so tiny that Einstein himself thought that these waves couldn't be detected. So gravitational waves were first described in this 1916 article by Einstein. But he got some of the details wrong, and it took several more publications before he actually got those details right. And I've just quoted here, I've translated from German, this first statement in the literature about gravitational waves. But until 1974, gravitational waves were just a theoretical prediction from the Einstein field equations. Then, in 1974, a pulsar was discovered called B 1913 plus 16. This is loosely shown in this diagram. This pulsar is a very compact neutron star, which is, pardon me, it's one of these two, which is orbiting a companion star, which is probably also a neutron star. These two stars orbit once every 7 3/4 hours. The orbit is eccentric, as you see here. And here's the fantastic thing. Hulse and Taylor, observing this system, discovered that each orbit, the two stars come closer together, 3.5 millimeters. So the orbit of this system is a few million kilometers across. It's about 4 times the size of our sun. Yet you can measure the orbit so precisely because one of these systems is a very precise clock. And this falling together is proof that Einstein was right. Because in Newton's theory of gravity, two stars that are orbiting just continue the same orbit forever. But in Einstein's theory, when the stars orbit, they emit some gravitational waves. Now in this case, the frequency of the gravitational waves is twice the orbital frequency, so it's tens of microhertz. But the system loses energy and the stars gradually fall together. So we know that gravitational waves exist because it's seen in this system. Now, think about this. After the system has done 3 orbits, it takes about 24 hours, 1 day, the two stars have come together about 10 millimeters, 1 centimeter. And so after a year, the two stars have lost enough energy to become 3 meters together. After 1,000 years, 3 kilometers. And after about 300 million years, these two stars will actually merge together and they'll form a black hole. And this is the kind of thing that we'd like to see with our gravitational wave detectors. A system like this Hulse-Taylor binary pulsar, but at the end of its life. In 1993, Hulse and Taylor received a Nobel Prize for their discovery. There's a plot here which simply shows that the rate at which the orbit is advancing in this system agrees exactly with general relativity. In fact, about 10 years ago, a similar system consisting of 2 neutron stars was found called the double pulsar. Both neutron stars can be seen pulsing. And so in fact, that gives much better constraints on Einstein's theory, some of our best tested general relativity. Okay, so we know gravitational waves exist because their effects are seen in the system. Now, how do we detect them? So let me start by showing you some pictures of the current generation of gravitational wave detectors. This is one of the laser interferometer gravitational observatory detectors in the United States. The first, these letters form the acronym LIGO, L-I-G-O. This one is located northwest in the United States, near the grounds of the Hanford nuclear reservation. This is what it looks like from an airplane. There's a central building here, and then these arms are both 4 kilometers long. What you actually see here is a concrete shell. And inside that shell is a long vacuum tube. This is the second LIGO detector. This is in the state of Louisiana. It's about 3,000 kilometers from the other detector. So it would take light 10 milliseconds to travel from one instrument to the other. This is a detector in Europe, the VIRGO detector in Cascina. This is from a French-Italian collaboration. It's also taken on members from some other European countries in recent years. And this is the GEO detector. This is a German-British project. It's operated by my institute. This is smaller than the other instruments. The arms are about 600 meters long. This means it's less sensitive. But it's been a very important place for developing technology. And the technology in the larger detectors was in large part developed and tested here at GEO. This is a Japanese detector that's now under construction called KaGra. This is being built in tunnels under a mountain, which reduces the shaking of the ground. And I'll describe later why that's important. It's on the same site as the Kamioka Gravitational detector. This was funded in 2010, and construction began in 2012. So how do these detectors work? To explain, let me show you first how gravitational waves affect things with a thought experiment. So you have to imagine that we're in space. We're just floating far away from the sun, from planets, from anything in space. Hopefully wearing a spacesuit so we have something to breathe. And we take some marbles, and we just lay them in a circle, very delicately. So they're just floating there next to us. Now imagine that a gravitational wave comes, for example, from a supernova that's far behind the blackboard. What will happen is these marbles will begin to oscillate in this pattern. It's a quadrupole pattern. The thing is that what I've drawn here on the screen is greatly exaggerated. And so, roughly speaking, if you were very close to 2 black holes or 2 neutron stars that were colliding together, this is what you'd see. But if you were far away, the effect is reduced by the ratio of the size of that object, a few kilometers, divided by the distance to us. And so that's 21 orders of magnitude for systems that are at megaparsec distances. So you don't see such big oscillation in our experiments. So gravitational wave detectors look for this motion using technology that wasn't available to Einstein. Ultra-stable lasers, electronic control systems. The way the instrument works is the marbles are replaced by these 4 masses. These are mirrors, and they hang from wires, which means that they're free to move along these axes. A laser illuminates these mirrors in an interferometer. By the way, for those of you who are physics students, this should look like something that you studied. Somebody tell me? Named after the American physicist Michelson. So what happens is that the light forms interference fringes at this photodetector. And if a gravitational wave comes from directly above, it changes the distance between these pairs of mirrors. It first decreases the distance here and increases the distance there, and then half a cycle later, the other way around. So the interference fringes at the photodetector move a little bit. And that motion is an observable signal. This is what the instruments actually look like. You don't see the mirrors and the lasers because everything is in vacuum systems. So there's big vacuum tanks And these are tall because the suspension elements are actually hanging inside here. This is an optical bench with a laser. This is one of the optics. I like fine mechanics, Swiss watches, diamond jewelry. And these things are like jewels. The surface of these mirrors is precise to nanometers. So that means that's roughly, you know, the height of a handful of atoms. So the average position of the surface of the mirror is incredibly precise. I think these things are like jewelry too, partly because of the price. These are almost unique pieces of optics. And this is a picture of people working inside one of those vacuum chambers. And you can see they're wearing bunny suits so they don't contaminate it, and there's a shield hanging around here. There's filtered air being put into there to keep things clean. Okay, so the effect of gravitational waves is very hard to observe because it's so small. So in the experiment, the thought experiment with the marbles, you saw these big deformations. And now you're supposed to imagine that the same thing is happening to our instrument. So here's the two arms of the interferometer with the laser, and here's the photodetector with the fringes. And as the gravitational wave goes by, it sort of stretches and shrinks the geometry of the space in between. But here's the thing. The change in the distance, the amount by which one arm gets shorter or longer compared to the total length, so delta L divided by L, is tiny. 1 part in 10 to the 21. So what that means is that the change in the length between the mirrors is 10 to the minus 16 centimeters. Now think about how tiny that number is. If you've ever worked in a machine shop and you've tried to do really good machining, you've maybe worked to 100th of a millimeter. That's a 10 microns. A really good machinist can do things to a couple of microns. And of course, if you've worked in optics and you build optical things, then you've done things to possibly nanometers of precision. But you know, an atom is 10 to the minus 8 centimeters in size. The nucleus of an atom is 10 to the minus 13 centimeters in size. This distance is 3 orders of magnitude smaller than the nucleus of an atom. When I first heard about this, I thought this is ridiculous. I mean, think about the mirrors, right? The surface of the mirror is a bumpy thing made of atoms going up and down by 10 to the minus 8 centimeters. It doesn't even make sense to talk about where the surface of the mirror is with that precision. But it works here because the light, the laser light, is illuminating the whole surface. And you take Avogadro's number to the 2/3, and there's 10 to the 22 atoms, or 10 to the 24 atoms on that surface. And so if you average over all of those, which is what the light's doing, you can actually determine the average position of the surface much more precisely than the size of a single atom. Anyway, the challenge of these experiments is that the distortion of space-time caused by gravitational waves is much smaller than what you see here. So the detector output is dominated, in fact, by instrument noise. So this is a plot showing the power spectrum of the noise. So the horizontal axis here is frequency. This is 1 hertz, 10 hertz, 100 hertz. This is 1 kilohertz and 10 kilohertz. So roughly speaking, this is the audio band. The frequencies that your ear can hear are 20 hertz to a few thousand hertz. And this axis here is showing the sources of noise in the instrument. And what you can see is that there's different sources of noise. At very low frequencies, shaking of the ground, seismic noise is the dominant thing. This is caused by ocean waves hitting the coastline hundreds of kilometers away from the instrument. It shakes the ground. At higher frequencies, for example, at the highest frequencies here, the dominant noise is shock noise. This is because if you're trying to observe a gravitational wave at the frequency of, let's say, 1,000 hertz, you have 1/1000th of a second to make that observation. And in that short time, a finite number of photons hit the mirror. And there's some uncertainty in how many photons that is, Poisson fluctuations, and the square root of that number gives rise to some fluctuating noise as well. So this dominates the noise at high frequencies. In the mid-frequencies, Brownian motion, the fact that the atoms that make up the mirrors and the suspension are not at zero temperature, they're shaking with thermal vibration, that's also a source of noise. And so if you add up all these different noise sources, you end up with a region around a few hundred hertz here, where the instruments are the most sensitive. Now, we're always working here in the low signal-to-noise regime. Because our instruments have these different fundamental sources of noise, and because the signals are so weak, we can't just look at the output of the instrument and see the signal there. You know, if you look through a telescope, you can see typically a bright star, a planet. It's just sort of obvious that it's there. But if you're looking at a very weak source, you might be staring through it and trying to see, is that really something that's genuine or not? And this is the kind of problem that we have with these instruments. So what I've shown you here is the output of a detector in blue, and a sort of typical signal in red is buried in this noise. So we have to try and search for it, like searching for a needle in a haystack, because we don't know what the signal looks like. So we have to search through many possible signals and try and find if the hidden signal is there or not. So a very important part of the instrument that goes at the output of the instrument is a computing system to search for these weak signals. Typically, we use match filtering to search for the different possible waveforms that we might find. And in fact, this is my contribution in this area. Myself and my group work primarily on the data analysis algorithms that run on these computers, as well as on the hardware for the computations themselves. I think I want to advertise a project that I run called Einstein at Home. Some of our searches are actually limited in their sensitivity by how much computing power we have. If we had more computing power, we could do our searches better. And so about 10 years ago, I created a project called Einstein at Home. This is a volunteer supercomputer. By the way, does anybody here actually use Einstein at Home? Any volunteers? Okay, then I'm advertising in the right place. If you Google for Einstein at Home, you'll find a web page. If you go to the web page, you can download an application for your computer. We have Windows, Linux, and Macintosh versions. And what happens is that when your computer is not doing something else, when it's idle, like my computer is right now, it actually downloads some data from one of our servers, and it searches it for weak signals. And it does this in the background. You don't notice it. And it sends results back. You also get a screensaver for free. It's disabled at the moment on my laptop, so you can see my talk instead of the screensaver. And this, we have now many, many people who signed up for this. We actually search not just LIGO data, we also search radio data from the Arecibo telescope and gamma ray data from the Fermi satellite. We found many new radio and gamma ray pulsars in this way. Just a little snapshot of how this works. We have some servers in Milwaukee, Wisconsin, the United States, and also some in Germany. We get data from these different sources. It goes onto our server, and then we distribute it on the internet. And some of our volunteers have provided pictures of themselves. And we have small children, American college students, extraterrestrials. This is interesting. This is a computer cluster in Chicago. About 1/3 of all the radio broadcasting in the United States is done by a company called Clearstream Communications. They have a computer cluster that to actually prepare their broadcasts. And the person who runs that is a fan of Einstein at Home. And so when they're not busy preparing the radio broadcast, he runs Einstein at Home on it. Okay, and I just wanted to tell you what the scale of this project is. I looked up the statistics this morning from our webpage. So over the past 10 years, we've had more than 400,000 volunteers from every single country recognized by the United Nations, even including North Korea, for example. There's been, in the last 2 weeks, more than 80,000 computers have gone to work from us and returned results. We use GPUs for their computing power. There's more than 22,000 GPUs. So currently, this system is delivering almost 2 petaflops of computing power. And just to put this number into perspective, I looked to see what the largest supercomputer in India is. And it's right here at the Supercomputing Education and Research Center. Probably some of you use that system. Just for comparison, that system is 0.9 petaflops. It's slightly less than half the capacity of Einstein at home. So our volunteer computing system is actually really a scientific enabling tool. Just because I don't want to hurt anybody's feelings, my comparison is not completely fair. And the reason why is because Einstein at home is not a high-performance computer, like a Ferrari is a high-performance automobile. Einstein at home is a high-throughput computer, sort of like a big dump truck. It does a lot of computation, but there's nothing that's very high-performance about it. Okay, so I've told you how gravitational wave detectors work. Now let me talk a little bit about the science that we hope to get out of these instruments. So our main motivation is simple. We know about the universe primarily because we study it using electromagnetic radiation. We have radio telescopes. We have X-ray telescopes. We have optical telescopes and infrared telescopes. But all of these telescopes have a common feature, which is they're sensitive to electromagnetic radiation, light, radio waves, and all of its different flavors. But they can't see certain things. For example, if 2 black holes are in orbit around each other, and they lose energy into gravitational waves and they merge together, we can't see that with these telescopes because black holes are black. They don't emit any light or radio waves or anything else. The only way we can observe something like that is using gravitational waves. So sometimes people say, well, gravitational wave astronomy is going to open a new window on the universe. I don't like that analogy because a window is something you can see through. And it's more like opening a door, where now you can see what's outside. The second motivation is better explained by one of my physics heroes, Richard Feynman, than by me. Feynman said, it doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. So the second motivation here is, was Einstein right? Is general relativity indeed the correct theory of gravity? I personally am a card-carrying member of the General Relativity Society. I'm not so interested in this motivation because I believe that Einstein was right. Still, it's an important thing to do. And studying gravitational waves will let us observe gravity in the regime where the gravitational field is strong, whereas most of our tests are not in that regime. So that's potentially very interesting. Now, what are the first sources that we expect to detect? The first sources are these double star systems, binary systems losing their energy into gravitational waves. In the entire universe, so the visible part of our universe is about 14 gigaparsecs in radius. That's the distance that we can see. It's called the Hubble horizon, or Hubble radius. Now, the initial LIGO instruments that were built and operated some years ago could see about 20 megaparsecs into there. And in that distance, the coalescence of 2 neutron stars, for example, happens perhaps once every 100 years. The rate's rather uncertain. If we could observe the entire universe at 14 gigaparsecs, this process would take place about once every 5 or 10 minutes. Anyway, what would this sound like if we could hear it? Remember I said the gravitational wave frequencies, the ones that we can detect with our instruments, are in the audio band, from tens of hertz up to kilohertz. So this is what it would sound like if you could actually hear it. Let me turn up the volume on my laptop first, that might help. Go back to this slide again. Okay, I hope it works this time. Oh, how disappointing, I'm sorry. Is the audio system turned on? If it is, let me just try playing it through my laptop. It's high frequency and it might carry. Let me try it without just to see if that works. Oh, I'm so sorry. It's my own fault for not testing this. Okay. I'll try and play that for you at the end if there's some time. But what you would have heard, if I'd done a better job of preparing, is something that sounds like this. It would increase in frequency and in amplitude, because as the stars get closer, they orbit faster, and the frequency of the radiation goes up, and so does the amplitude. The gravitational waves get stronger. Okay. So similar signals would be produced by the coalescence of a compact object like a black hole with a neutron star, or two black holes. By the way, you might wonder, well, what about ordinary binary stars, white dwarf stars or ordinary stars? And the problem is that those stars are too big. They do indeed lose energy and spiral together, but the stars are so big that they finally merge together long before they emit gravitational waves that are high enough in frequency for us to observe them. So we can only see small objects. Those can get close together. So the waveform has three different phases. There's an adiabatic in-spiral phase here that can be computed using post-Newtonian approximations. There's a merger phase here which requires numerical relativity to compute. And finally, there's a ring down at the end here, which is basically just a damped exponential. And we search for these signals using a match filtering technique that hunts for the waveforms that correspond to different masses of the objects, different spins, different sky locations, and so on. When we eventually detect these signals, comparing the waveforms to these predictions will give us a very good test of strong field gravity. The observations can also be used, for example, to calibrate models of stellar evolution, because we'll be able to count, for example, how many neutron star binary systems there are in the universe. And this is an important input for understanding how stars form. Another possible source of gravitational waves is rapidly spinning neutron stars. If they have a bump on them, a mountain, or if they're wobbling, or if they're accreting matter in nearby stars, then they produce continuous gravitational waves. And these continuous gravitational waves, these go on constantly over years, decades, centuries. These can be detected by integrating the data set for a very long time against a copy of the waveform. If we can detect these signals, we can learn something about the structure of the neutron stars. For example, neutron stars sometimes undergo glitches when they're spinning. They suddenly change their regular rotation. They start to spin at a slightly different rate. And that's probably because there's something like I can't call it an earthquake, a starquake on the surface where the crust and the interior of the star rearrange themselves. It changes how the way the star rotates. We can see the gravitational waves. We might learn something about that mechanism. So it's easy to search for signals from known pulsars. And in fact, the previous generation of LIGO instruments did exactly that. And some of the results, I think, are quite remarkable. I think I won't talk about these right now because I think this is a matter for the experts, and those in the audience here probably already know this. I will say that searching for these types of signals from these rapidly spinning neutron stars is an extremely difficult computational problem. And this is actually what Einstein and is doing. And the reason why is because our detectors are on the Earth. So these spinning stars emit a very continuous signal. And if our detectors were just floating in space, the data analysis would be easy. Take a Fourier transform and look for peaks. But the detectors are sitting on the Earth, which is spinning around its axis and orbiting around the sun. And that motion modulates the signal. And the modulation depends upon where the source is on the sky. So we have to search first for a signal from that point in the sky, then from a signal nearby, then for a signal near that. And there's a lot of points in the sky. That's when we need large computing systems. Another possible source of gravitational waves is what I'd call burst signals. For example, here you see an image of a supernova that took place in 1987, called supernova 1987A. Unfortunately, events like that in our galaxy only happen about once every 100 years. And we couldn't observe these events if they took place in other galaxies. They'd be too far away. So this is the type of signal that we could observe, but unfortunately, it doesn't happen often enough that we can really count on it. Now, there might be other sources of short transient signals. For example, if two massive black holes merge, that produces a rather short signal, the very end of that waveform that I showed you before in our detectable band. It could be that a neutron star collapsing to form a black hole, if it's accreted enough mass, might do something like that. Or there might be exotic sources. For example, cosmic string cusps could produce short bursts of gravitational radiation. The main method that we use to look for these is we look at time frequency maps for excess noise. And finally, the topic that got me interested in gravitational waves in the first place is the stochastic background. As you probably know, we know that our universe started with a Big Bang, had an early hot phase, because in 1965, Penzias and Wilson discovered electromagnetic background radiation. This is leftover radiation from an early hot phase in the universe. There might be a similar background of gravitational radiation. And to me, the exciting thing is the gravitational radiation would come from much earlier times and really be unmodified. The microwave background radiation, the electromagnetic one, shows us a picture of what the universe looked like a few 100,000 years after the Big Bang. If we could detect a neutrino background, that would show us what the universe looked like perhaps a second after the Big Bang. But gravitational waves, because they're so weak, because they interact so weakly, would actually give us a picture of what the universe looked like much earlier than that. So if we want to know what the universe looked like 10 to the minus 14 seconds after the Big Bang, we could learn that by studying gravitational waves with frequencies of a millihertz. And if we want to know what the universe looked like 10 to the minus 20 seconds after the Big Bang, we could do that by studying gravitational waves with frequencies of hundreds of thousands of hertz. Now, I think the prospects to see this background in the next generation of gravitational wave detectors is not good. Nevertheless, in the long term, the analogy of what Penzias and Wilson discovered with the electromagnetic background would be a picture of the very early universe that we couldn't get any other way. And I'll just comment that more than a year ago, the BICEP-2 experiment announced that they had seen signs of a primordial gravitational wave background. Unfortunately, those claims turned out to be wrong. They've been misled by emission from polarized dust in the galaxy, which they hadn't properly accounted for in their analysis. I repeat the question. It's a good question. The question is the signal always there, or is it just for a little while? And the answer is, it's always there. So, you know, these days television sets are too good. You turn it on, you get a clear picture, and so on. But when I was a kid, the television signals weren't carried by cables, and they weren't digital. They were analog, and they were carried by radio waves. And so when you turn on your TV set, if it was a good channel, you got a nice clear picture. But if it was a bad channel, you got this kind of gray static on the screen, kind of hissing noise. And in fact, actually, some fraction of that hissing noise is actually the electromagnetic background radiation. So the signal is something that is present always. It's always there. It's a sort of stochastic random thing. And if you had a really long lifetime, if you could wait 1 billion years for the universe to get a bit bigger, then you'd find that the amplitude of that radiation would go down somewhat. So it varies over the time scale of the universe, but not over our time scale, over the human lifetime. It's just always present in the background. Does that answer your question? Okay. Please ask me stuff, because I'm going to run out of slides pretty soon. I'll have to give the flowers back to them. So I've been working in this area for more than 20 years, and so far we haven't made any gravitational wave detections. But I just wanted to say that the data analysis, and so sometimes we're asked, well, are you sure that the data analysis methods that you're using actually work? Maybe there's signals there that you've missed. And in fact, we have shown that the methods work, and in fact, we've applied those methods to other kinds of data, to electromagnetic data, for example, from radio telescopes and from gamma ray telescopes, and for example, discovered many, many interesting new pulsars using these techniques. Some of the methods are also used, for example, in the data analysis pipeline of the Kepler satellite. Kepler has discovered several thousand exoplanets, and some of our data analysis methods are actually part of the pipeline that's used by Kepler. So far we don't have any science results, but we're confident that our methods work, and what we need really is better data. So let me talk now about the future, about what's coming soon. I'm very optimistic about this. In the United States and Europe, a new generation of instruments has been constructed. This, for example, shows one of the pieces of the advanced LIGO instrument. This is suspension. One of those mirrors that you saw in an earlier picture is hanging here in the bottom stage. And this whole structure is a kind of shock absorber, like in a car. So the idea is that the ground shakes, but this suspension acts like a mechanical filter. So when you shake the bottom, the shaking doesn't get transmitted down to the mirror at the end of this. We operated a first generation of the LIGO instruments until 2010. And then the instruments were removed, and a new generation of instruments was put into place. The construction of those finished in 2014. There was a period of commissioning. And just a bit more than 1 month ago, in mid-September of this year, we started our first science run using this new generation of instruments. The sensitivity improvements here are dramatic. So for example, at the moment in our very first science run, we can already see, we could see the coalescence of 2 neutron stars at a distance that's about 3.5 times greater than in the previous generation of instruments. Now, a factor of 3 improvement doesn't sound like something to get excited about, but this means that we can see a volume of space that's 3 cubed larger. Because of course, 3 times the radius encloses a much larger volume. For more massive systems, for example, of 2 black holes, we can actually see those now at distances that are about a factor of 6 greater than before. So that's more than a 100-fold increase in the volume. And so correspondingly, much higher likelihood of observing signals. Yes?
Why can't we have detectors in space, saying LIGO detector? Because you say when it's placed on the ground, it shakes. Enough for
Good question. So eventually we will. But the one-word answer to your question is money. It's very expensive to build experiments in space. And for example, one of the signs of the tremendous progress in science in India is the fact that India now flies scientific space missions, like AstroSat successfully. I mean, the level of, when I was an undergraduate, I'm sorry, I'm getting off topic, but when I was an undergraduate, I did experimental physics. And I built electronics. I was originally going to be an electrical engineer. And I learned very quickly that whenever I built something, it didn't work. And roughly when I was in university, I learned to build electronics that did work. First we built the power supply, and That didn't work, so you fiddled and figured out what was wrong and fixed it. Then you built the next stage of the circuit, which didn't work, and you fiddled and got that to work, and so on. And it was only by actually putting your hands on something and working with it that you were able to get it to work. And a satellite, a space mission, is this incredible thing. You build it on the ground, then you shake it really hard, you subject it to accelerations a few times bigger than the force of gravity, you throw it into space, and it works. That is just amazing. And it requires an incredible level of technological sophistication to build something that can do that. So the short answer to your question is it's very expensive to do that. It is part of the future plans, and I'll talk about it towards the end. Okay. So before continuing, I need to explain something about gravitational wave detectors. So normal telescopes, the Chandra X-ray satellite, Fermi Gamma Ray satellite, Arecibo radio telescope, these things can point. In either the field of view is small, like Arecibo, so you know that your source is somewhere directly over this beam, or they have a very narrow point spread function, like Chandra. So you can identify where the source is. Gravitational wave detectors are different than this. They have a response that's more like an antenna. They have like an antenna function. So this antenna function, here's the observatory in the background with two arms. And you're most sensitive directly overhead or directly underfoot. And you have no sensitivity, for example, in certain directions along the plane of the arms. But these are like antennas. They gather signals from all directions in the sky at once. So with one gravitational wave detector, you couldn't tell the direction to a source. And if we detect signals, we'd like to know where they're coming from. So the only way to find the sky position of a source is using triangulation. For example, if you have a source here in the sky, the gravitational waves would arrive first at the instruments in Europe, GEO and VIRGO, and then, perhaps about 20 milliseconds later, at the gravitational wave detectors in the United States. So the time offset in the arrival times lets you figure out where the source is on the sky. Now, if you have only two instruments, you can't do that. You can confine yourself to a circle. It's only with three instruments that you can really identify the sky position precisely. So all of the different experiments, with the exception of the KaGra instrument, have a data sharing agreement where they share data exactly so that they can figure out where the sources are. Now, originally, the LIGO project had planned to build two detectors at one site in Hanford and one detector at the other site in Livingston. But a few years ago, we changed course. One detector was installed in Hanford, and the other instrument that had been planned there was put into a warehouse. And we would like to put that third instrument somewhere, ideally in India, which is far away from the other ones, because the triangulation will work best if we can put the instruments widely separated from each other. So if we could put one of our gravitational wave detectors in India, we'd get much better identification of location of signals. So for example, these blue ellipses here show the error regions. The error in trying to determine the position of the source if we only have the instruments in the United States and in Europe. If we could add another instrument in India, these error regions would get much smaller, because this bigger baseline for triangulation would let us do much more precise determination. So many Indian scientists have made important contributions to this field. Two of the pioneers, Professor Durandar, Professor Iyer, are both here. They're both retired now, but their scientific children and their scientific grandchildren, I think you're one of them, work around the world on this topic. And the scientists in India have formed a collaboration It includes a dozen of the best research institutes and universities and laboratories. And the goal is to build a third LIGO detector here in India. The United States has agreed to provide this detector that's sitting in a warehouse. It's worth something like $70 million. India has to provide the site, the vacuum systems, and the personnel, the scientists and the engineers, to operate this facility. The proposal has very broad support in the scientific community, and it's under consideration now at the highest levels in the Indian government. I'm very hopeful that this is approved. If this is approved for in this year or in the coming year, then a third LIGO instrument in India should be complete by 2022, and then taking part in these efforts. Yes?
Be associated in any way with gravitational waves? Like, is it like in fields we have direction-dependent properties around it, like we express it as a tensor magnetic fields. So can anisotropy be associated with gravitational waves like in any sense?
Let's see. Let me think about that. I'm trying to answer you after my talk. It's a good question, but I don't think I know the answer off the top of my head. Okay, so when will we make our first detections? We don't know this. The number of sources is uncertain. But we expect to increase our instrumental sensitivity over a period of several years. We're currently doing our first observing run. That's 2015, which is going to last, we've decided to extend it to about 4 months. And for example, we can see double neutron star systems currently up to a distance of about 75 megaparsecs. And there, the number of double neutron stars that we might detect, we're not sure. It's somewhere between 0 and perhaps a few. It depends on how dense those systems are in the universe, which we don't know. Now, there's better prospects, perhaps, of detecting other types of systems, more massive systems of black holes, but we know very little about the rates. Nevertheless, by roughly 2019, when we're operating the instruments at their design sensitivity, when they can see double neutron stars at distances of 200 megaparsecs, at this point, we're quite confident that we can see at least one event, and perhaps many. Okay, I had planned to say something about the prospects for joint observations with electromagnetic instruments, but I'm hoping that people here will have questions. And so I'd actually like to try and bring my lecture to a close. So if you have questions, you can ask them, or if you want to get home and enjoy the afternoon, you can do that as well. Yes, please. Yeah.
What is the significance of these gravitational waves? Significance and salient features of these gravitational waves. And I also want to know, if suppose we don't get these waves in plane of the instrument you have placed, will these gravitational waves get diffracted, and is it identified?
Yes, so these questions I can't answer, I'm happy to say. So gravitational waves are no different than other waves. So they're characterized, for example, by an amplitude and frequency. You can split up, you can have an arbitrary waveform, and it will propagate through space. There's no dispersion, because gravitational waves of any frequency travel at the speed of light. So in principle, you could build a box called a gravitational waveform generator. You could feed a waveform into it. It would produce a gravitational wave. There's two polarizations. And you could produce these waves just as you produce electromagnetic waves or sound waves, and then fly off through space. So for example, a very advanced civilization might use these things to communicate. I don't know why they want to do that. Maybe to keep themselves hidden from less advanced civilizations like ours. They can't detect them.
Thank you, sir.
That was the answer to the first part. Sorry. Gandhi was once asked what his opinion of Western civilization was. He said he thought it would be a good idea. The answer to the second question was, just remind me what the second part of your question was?
Can it be diffracted?
Yes. So gravitational waves in principle could be diffracted. But you need an enormous amount of mass to do it. So gravity is the weakest of the forces, and that means that gravitational waves basically travel undisturbed through everything. But in principle, if you took very massive objects, compact objects like black holes, and you arranged them, for example, in a crystal structure, you could do diffraction in the same way that you would diffract electromagnetic waves with regular lattices of charges. Okay. Let me just try and wrap up. I think I'm not going to talk about combining gravitational wave with electromagnetic observations. It's a bit of a long shot anyway. I'd just like to briefly say a little bit about the future. So in the long term, we're carrying out design studies funded by the European Union for a third generation detector called the Einstein Telescope, which could still see another factor of 10 farther than these ground-based instruments that we're building now. These could see a substantial fraction of the visible universe. And so with an instrument like this is underground to minimize the seismic effects of the shaking of the ground, we'd be able to observe all of the binary neutron star coalescences in our entire universe. So we see these every few minutes in this instrument. There's studies underway now in the United States, perhaps thinking about building a similar instrument there. We're also hoping to put a low-frequency instrument called Ruthe into space. This would be sensitive to gravitational waves in the frequency range from millihertz up to a fraction of a hertz. This is now planned as the third large ESA mission called L3 for launch in 2036. A technology pathfinder satellite is going to launch on December 2nd, sometime between 9:30 and noon Indian time, which is going to test the technology to be used in this. And if LISA Pathfinder is successful, it might actually advance the schedule for doing this. So we will eventually have gravitational wave detectors in space, but it's still many years in the future. Okay, there's many other topics here. Detection of gravitational waves, for example, using pulsar timing arrays that I haven't had a chance to touch on. I'd just like to conclude by saying that I believe that by the end of this decade, our network of gravitational wave detectors will make its first detections. The most likely sources are the coalescence of compact binary stars, neutron stars or black holes. We'll be able to determine where these are on the sky with some precision. I hope we'll be able to do that better in the future with a LIGO instrument in India. And just finally, the last prediction that the first detections of extraterrestrial X-ray sources were made in the early 60s with experiments that were flown on balloons. And within 40 years after that, we had the Chandra Telescope, an incredibly sensitive precision instrument with arc-second resolution that's revolutionized our understanding of many astrophysical processes. I believe that after we make the first gravitational wave detections, the scientific world will see clearly the future of this field, and probably within about 40 years after that, we'll have very sensitive instruments that give us a lot of insight into astronomical processes that we couldn't study any other way. So thank you very much for your attention, and if you'd like to contribute to this effort, please sign up one of your home or office computers to Einstein at Home.
Thank you very much, Bruce, for this excellent exposition on gravitational waves. So I assume would you be willing to take a few more questions?
I would love to, yes.
So, floor is open for questions. Okay. We have some volunteers with mics, so it would be nice if you could wait for the mics.
Hello. This is something personal about your training under Hawkins. How was that experience?
It was a very good experience. I was an undergraduate in the United States. I went to MIT as an undergraduate. And originally I wanted to study electrical engineering. And I got interested in physics the summer before I went to university. I read some physics books and decided that this was more interesting than electrical engineering. So actually not true, though. You're both very, anything is very interesting if you study it properly. And at first I was an experimentalist. I built a microwave experiment to study the background radiation, X-band microwave electronics. And that work takes years to do, and as I was doing it, I was thinking I'd really like to understand better, for example, where the microwave radiation comes from. And so I got interested in cosmology, and ended up getting a scholarship to go to Cambridge. And it was a very good experience. Stephen was already quite famous at the time I was a student of his, but because of his disability, he couldn't travel so easily. He was kind of stuck with us, the students. And it was a very, very nice environment. All of the students' offices and Stephen's office were on this large tea room. And tea was at 11 and at 4. And the tea room had these white formica tables you could write on. And so a lot of my graduate education took place in the tea room, where Stephen would participate along with everybody else in the group. And there was a lot of feedback. So you couldn't go along the wrong path for very long before it would come out in a tea room conversation and somebody say, you shouldn't be studying this paper because it's rubbish. Read this instead. Or there's an obvious mistake in what you've done here. And in the last year, I became Stephen's senior graduate student. And Stephen could speak in those days, but his voice was very monotonic. And so it took a while before you could understand him. So I got to travel around the world with him, basically acting like a translator, and got to meet a lot of very good physicists and take part in some interesting conversations and so on. So a good experience. Yes.
My question is, see, in electromagnetic wave, we have the concept of particle wave duality, right?
Yes.
So in the case of gravitational wave, do we have any evidence to believe that there are particle possibilities? And do we have a duality there?
So let's say that there's no evidence. So there's evidence, for example, that light has a wave-particle duality. For example, there's experiments where you shine light through very thin slits. You make an interference pattern, and you can put down photographic film, and you record individual spots where the photons arrive. So gravitational waves should be analogous. There should be particles called gravitons, which are the gravitational equivalent of photons. But there is no experimental evidence for the existence of gravitons. I have no idea how we detect them. Maybe that's the short answer to your question. So yes, there should be such particles. No, there's no evidence for their existence.
Okay, thank you.
Sure.
Sir, you are given an instant myth. Newton's gravitational force, apple falling inside. He said, this in imagination only that the Newton space or experiment space, no apple, a tree like that. I read it in this one. Like that, another Eastern myth, this Darwin theorem, and that is migration or human habitats, Europe and other countries. This is not existed before BC. After this one only, this one. Then Einstein equation itself, one assumption is taken. M is equal to M0 divided by root of 1 minus c square by v square. Sorry, v square by c square. About physics, we are thinking is a physical science, cannot be taken assumptions. But this way going means human habitats and science, migration, Stone Age, like that Einstein and
Newton. For longer philosophical discussion, which we could continue after a coffee break.
Okay, anyway, symptoms and abstract you can answer. Not
Okay, I think this is a subject for discussion later.
Cosmic microwave background radiation, of course, is thermalized.
Yes. Yes.
The cosmic neutrino background is relatively thermalized. What about the cosmic gravitational wave background?
Very good
Because
question.
systems also are
Very good question. So because gravitational waves interact so weakly, they never had time to come into thermal equilibrium. This was a point that was first made by Landau many years ago, that because the gravitational interaction is so weak, the gravitons never had a chance to thermalize. And so the spectrum of the gravitational wave background will not, we expect, be a thermal Planck spectrum. It will be something else. And the shape of that spectrum tells us something about the processes that happened early on. So it's almost like nature gave us a gift, because by not thermalizing that spectrum, a thermal spectrum has the maximum entropy for given energy. That is, say, contains no information whatsoever. Whereas the gravitational wave background is probably not thermalized. That means it's got some information in it. So anyway, no, it's not expected to be thermal. We don't know what it would look like, and it would tell us something about the Earth universe.
So follow-up question, connecting with the question about anisotropy which was asked here. So other radiation which are thermalized, we talk about anisotropy in terms of the temperature correlations. Since now it's not thermalized, what is the way you would like to parameterize to talk about gravitational waves from different parts of the sky?
Okay. So your question has been answered for you.
It's been asked.
I couldn't do it.
Reformulated, not answered.
Yes. So I'm not sure I can answer exactly the question, but let me do my best. So for example, if we look at the microwave background radiation right now, it's 2.7 Kelvin. That's the temperature of the electromagnetic background radiation. But if you look at it very carefully, you discover that it's actually a little bit warmer in one direction and a little bit colder in the other direction. And that's because our planet and our galaxy are actually falling towards a nearby cluster of mass. We're being accelerated towards that. And that it's actually speeding us up with respect to the cosmological rest frame, the average position of everything in the universe. And so there's a little bit of anisotropy in the electromagnetic background because of that. And then there's still finer anisotropies which come about because of the way that matter was clumped and clustered early in the history of the universe. In principle, there should be similar anisotropies in the gravitational wave stochastic background, in principle. But I'd say we're very far away from observing those. We're still very far from just observing the background itself, the equivalent of 2.7 Kelvin. So we're kind of getting ahead of ourselves if we start to talk about what's the structure underneath that. But yes, that should carry information, not just in, say, the spectrum of the radiation, but also in its anisotropy, how it looks on different parts of the sky.
My question is, can naked singularities be a likely gravitational wave source?
That's a very good question. I think I probably don't know the answer. We don't know very much about naked singularities because singularities are places where Einstein's equations break down. And that means that we lose predictive power. So I guess I don't know the answer to the question, and neither does anybody else, because by its sort of definition, naked singularity doesn't let you do predictions. I should say it's believed now that there's something called the cosmic censorship theorem, which was proposed probably by Penrose, and which states that naked singularities are always hidden behind event horizons, so that which keep them from being visible or affecting the universe. So I don't know the answer to your question, and I'm not sure that the question has an answer at the moment.
Gravitational waves are present all the time, right? So why haven't we been able to detect it yet, in spite of having instruments?
It has to do, there's a wonderful, does anybody know Sidney Harris? Sidney Harris is a cartoonist. There's these wonderful physics cartoons. And there's a great cartoon. It shows, there's this big supercomputer in the background. There's two scientists wearing white lab coats, sort of sitting in front of it, twiddling some knobs. And the whole picture is distorted. The computer is kind of a bit wavy, and the people are kind of a bit wavy. And one of them saying to the other, have we seen gravitational waves yet? The trouble is that waviness is very small. So there are gravitational waves going through us this very moment. There are gravitational wave signals registered in the output of our instrument, but we can't distinguish them from the noise, from what comes about because the instrument is shaking from thermal motion. That's all, it's just because it's so small.
So you mean to say that we don't have sufficient instruments to detect them yet?
Sufficient sensitivity, that's right. So imagine that you're trying to listen to a radio broadcast in India from halfway around the world. Okay, if you're a shortwave radio operator, you might be able to catch that signal. It's bouncing off the ionosphere. And so it bounces back and forth and eventually reaches you. But then, as you're listening to it, the signal fades out. You lose it. It's just not strong enough to detect. And so right now our instruments are just reaching the point where we expect to make detections. People started building gravitational wave detectors in the 1960s, but they just weren't sensitive enough.
Thank you.
Sure.
What are the techniques being used to suppress the quantum noise?
Oh, that's a very sophisticated, it's a very good question. And I'm the wrong person to ask. I can only tell you the words. So the main technique that's in use is something called squeezing. If you look at a harmonic oscillator, a quantized harmonic oscillator, and you put it in its ground state, there's uncertainty in both the position and the momentum. And roughly speaking, if you make a phase diagram where you show momentum in one axis and position in the other, the position of the oscillator isn't well, the position of the oscillator in phase space isn't well defined. It's not a point in that diagram, it's kind of a blob. And the uncertainty in the blob is a Gaussian, which is spread, roughly speaking, equally in position and momentum if you use the right coordinates. And because of the Heisenberg uncertainty principle, you can't reduce the uncertainty in the product of position and momentum below h bar over 2. But you can put the oscillator into other states called squeeze states, where, for example, the uncertainty position is smaller than it would be in the ground state, but the uncertainty momentum is larger. So you get something like an ellipse of uncertainty in the parameter space. Those are called squeeze states. And so one of the techniques that's been developed now to reduce the noise in gravitational wave detectors below, for example, this shot noise limit that I was talking about in high frequencies, is to squeeze the light. And basically, this lets you make a more precise measurement of the position at certain instants in time. And you lose information about the momentum, but you didn't want that anyway. So techniques like squeezing the quantum state of light are used to increase the sensitivity. But other than that very crude explanation, I can't tell you much about how they work.
So regarding the Einstein at home thing.
Oh, yes.
So apart from getting the free screensaver, will you put my name on one of the gravitational wave sources if I give you my computer?
That's a good question. So the International Astronomical Union has taken away the ability of scientists to name astronomical objects after people. We're no longer allowed to do that. I know, it's a shame. So first of all, if your computer, so Einstein Home Volunteers, and so far their computers have discovered more than 60 radio and gamma ray pulsars. And every one is discovered by at least 2. Because you see, people's computers don't always work correctly. And so all of the work gets sent always to computers owned by at least 2 volunteers. All the work gets done twice so we can check it. And so we do tell our volunteers when their computer discovered something. We send them a very nice certificate. And we put their names in the acknowledgments to our papers. So we say the computer that found this. So if your computer discovers a gravitational wave source, your name will go down in history in the paper, in the acknowledgments, as the owner of the computer that found that, but we won't be able to name the star after you.
sensitivity of the instrument, can we somehow use resonance, like it's at a very low frequency, you can absorb, can we somehow use the concept of resonance and frequency matching to increase amplification?
So this is again a subject. The answer, I believe, is yes, but I don't think I can tell you the details because I don't understand it myself. This technique can be used in tuning. These instruments are, in fact, have a lot of different resonances in them. For example, the light from the laser goes into the two arms, and I drew the arms as these mirrors hanging from wires. But actually, the arms are cavities. So the light bounces back and forth many times. Typically, in the instruments, it bounces back and forth 50 or 100 times, which makes the effective length of the arms, say, 200 or 400 kilometers. And so that cavity has certain resonance properties. And then there's other cavities that are used to collect some of the light that goes out the output and send it back into the instrument. These are called the signal recycling cavities. There's another one called the power recycling cavity. All of these cavities have resonances. And by tuning these to match each other, you can actually make the instrument more sensitive at some frequencies by sacrificing sensitivity at other frequencies. So yes. So for example, if we found one day a spinning neutron star that was emitting gravitational waves, let's say at 150 hertz, we could actually change the way the instruments work. We could modify the suspensions and the feedback and control systems to try and improve the sensitivity right at that frequency, right around 150 hertz. We'd be less sensitive to other frequencies, but more sensitive there. So it is possible to tune the different cavities, the optical cavities that make up the instrument, to make it more sensitive at particular frequencies. Yes?
You mentioned about different sources for the gravitation waves. So if we have different sources for EM waves, then there is an interference. And you are using the matching for detecting the gravitational wave. So if there is an interference due to different gravitational sources, will the matching will work, and are you taking care of it?
So there's two different meanings of the word interference. The first meaning of the word interference is I'm in my car tuning the radio, a particular station. But I can't hear it very well because another nearby radio station keeps creeping in, and so I keep hearing both of them. That's one kind of interference. And you know, that kind of interference is, for example, you look through a telescope and you're trying to see a source, but there's another star that's nearby and it's very bright. And so it's hard to see the one that you want to see because of the other. That's one kind of interference. And one day when our gravitational wave detectors are sensitive enough, we'll have to worry about that kind of interference. That is to say, we'll be getting multiple signals from multiple gravitational wave sources, and it'll be hard to tell one apart from the other. So that kind of interference, yes. Now, that's not a problem right now because our instruments aren't sensitive enough. We can just detect one source and be really happy. There's another kind of interference, which is in physics, if you have two waves that have exactly the same frequency, then the amplitudes add together. And they can add together in phase or out of phase. And so, for example, you can get patterns like interference stripes and so on. Now, this could also happen with gravitational waves, but it's very unlikely. Just think about how you do that in the lab. You take a source of light, maybe a laser, and then you bounce some of it off a mirror so you can mix it back with itself. And that's what you can't do with gravitational waves. I mean, to make a gravitational wave mirror is something that we don't know how to do, and that probably doesn't happen in nature either. So it's very unlikely that you'd have a gravitational wave source where there is another source which is exactly synchronized in frequency and phase so that you can get that second kind of interference.
I don't mean to sound overly pessimistic, but what if you can't detect them after all those years? Will you have to conclude the theory is wrong? Because there is other evidence that the general theory is right.
That's a good question. I'm an optimist. Life is too short to be a pessimist. And so I really believe that these instruments are going to work and that we're going to make these first detections. Now, let's suppose we fail. For example, suppose that we fail to discover the signals from these double neutron star systems, like the Hulse-Taylor pulsar system. What that means then is it would mean that, what I think it would mean, I mean, it could either mean that, for example, gravitational waves don't exist, that we're wrong in our understanding of them, or it could mean that the universe doesn't contain as many double neutron star binaries as we think. As a card-carrying believer in Einstein's general theory of relativity, I would much rather go with the second explanation than the first one. But just in general, I simply believe that we will make these detections. So I guess if we don't make them, it could mean that general relativity is wrong, but we have many tests, as you said, that general relativity, indication that general relativity is correct. Or it could mean that our understanding, for example, of stellar evolution and the formation of compact objects has got something wrong with it. That's the more likely explanation.
Okay, last question.
You said that the next You said that the next generation detectors were underneath the crust. How will that be efficient? Because isn't the crust more active at lower, deep inside the earth than at the top?
So I know very little about geology, but my understanding, what I've been told, is that the main sources of noise for us are, there's two kinds. There's earthquakes. That's when the Earth's crust rearranges itself. And we see these events in our instruments. They're sensitive enough that they see earthquakes basically almost anywhere in the world if they're strong enough. And then there's another kind of motion of the Earth's crust, which is just caused primarily for us by waves hitting the coastline. And that shakes the ground enough that it propagates through. But those waves apparently travel near the surface. They don't travel deep down. So, for example, the KaGra instrument in Japan is being built underneath a mountain. It's actually above the surrounding land. It's above sea level, but it's under a mountain. So what happens is the seismic waves, as they propagate through the Earth's crust, they actually go over the mountain, following the mountain, and they miss the detector, which is sort of underground. So it's a bit like if you've gone swimming in the ocean, and it's choppy and so on, and there's waves on the surface, and you hold your breath and you just go under, and suddenly it's calm. This is what I've been told by people who understand these things, that by going underground, we minimize these troublesome waves for us, the surface ones.
Okay, so looks like there are no further questions. Please join me in thanking Professor Alan for this. And on behalf of the International Center for Theoretical Sciences, let me thank all of you taking that time to join us today. And I hope to see you at the next Einstein lecture. Thank you very much.